more time since we are prepared to hear from Ameya Prabhu, who is a PhD student at Tor Vision Group in Oxford. And you may know him from the GDAM work, which got a lot of attention, I would say, in continual learning. And I really liked it also. As I was saying, Ameya will talk about navigating hurdles for online continual learning in the wild, from correlated labels to having no training data. So I'm quite excited about this talk. And please, Ameya, the floor is yours.
Amazing. Is my screen now visible?
Yes, perfect.
Awesome. So hi, everyone. I'm Ameya, and I'll be talking about navigating hurdles for continuing learning in the wild and focusing on the online setting. First, a brief motivation for the talk. This is quite experimental a talk, so feedback would be nice. The backstory for this talk is something like this, that I gave my first broader talk a couple of weeks ago at Computer Vision Talks, and I asked for a bunch of feedback on like how the talk would be. And people sort of asked like, well, like this is a good summary of your works, but like, how do you look at problems? How do I look at problems? Like, and my general reply was like, well, how I look at problems is like more or less informed from like how my advisors sort of like drilled into me how to look at problems. But I present a sort of a view of like, well, what do I how do I approach continual learning research, and that is this talk. So it's going to be 3 parts: methods, evaluation, problem setup, and I'll highlight one component in each of them. First, let's just dive into methods because time is short. Yeah, so how do I sort of like go about continual learning methods? Well, I sort of like to pose continual learning as like treatment effects. So what people do is that they come up with this novel idea A. They typically add it to the state of the art pipeline P, and they evaluate. If the E plus A performs better than P, then they write a paper. The reviewers recognize how smart they are, and they publish. Except a large fraction of continual learning papers would like follow this trend in some sense. However, this is not how it works usually. Usually people come up with an idea A, they add it to the pipeline P, and then it breaks. Then they come up with incremental changes, and then they evaluate A plus I1 plus I2, add it to the pipeline P. Then they write a paper, reviewers recognize how smart they are, and they publish. What is wrong with this? The wrong with this is, the part which is wrong is that A was the novel idea. However, all performance improvements come from I1 plus I2, etc. This is sort of the crux of the issue, that if I have to say one issue I have to point out in methods, then this is sort of the crux of the problem. Well, people say, why not ablate A? The issue is, ablation of A won't work because we chose I1 and I2 which were specifically tailored for A. So of course, when we remove A, something degrades. This sort of doesn't really mean A is needed. Hence, my skepticism. So this is sort of the general, if I had to sort of contextualize what general problem I have with methods, this is the one problem I have. What are the preliminary takeaways? So I have been telling this in some form or the other around years, and people say like, well, novelty is overrated, and we should be more radically skeptical of these complex approaches. They need to really justify the extra burden. One more thing people can people take away, and this is obviously correct, is that best practices remain stable. This is a trend that we see, that people propose these tricks, etc., and they remain stable. They sort of like constantly improve performance across methods, across these novel methods A. This sort of shows that incremental tricks which generalize are the sort of things which are driving the field forward. So these two are preliminary takeaways, but this is not what I just want to say. Like, simplicity is better, but we sort of need to go one step ahead. And sort of this is how I sort of approach papers. We need to sort of think about this as hypothesis testing, where methods are interventions. You form a hypothesis that, well, something is wrong because of this reason. Then you propose an intervention being like, well, I'll propose a method which sort of targetedly solves this one task, and I'll test it, and I'll benchmark it, and I'll see results, and I'll see how it performs. This is sort of the philosophy I've been following in the methods I propose. Say, for example, GDOM was just the hypothesis were sort of like, well, methods don't use the online stream. So what if I just remove the online stream and just test on it? The second hypothesis was, well, if any method has a performance degradation over time, then if you just extend time to very long time spans, the performance sort of drop to random. And we tested these two hypotheses in that paper. In the budget CL paper, which we wrote in CVPR 23, the sort of focus was on, well, like methods have sort of focused on this limited compute scenario. What if we sort of shift it to like all compute but limited limited memory scenario? What if we shift it to all memory but limited compute? Do they generalize? Like, this was the specific idea we tested, and like hence the solutions we got were sort of simple. Like, simplicity comes for free when you think of methods as hypothesis. You're targeting one specific problem that you want to sort of analyze, and as a byproduct, and this happens as a byproduct of this focused question asking. That's also my excitement about this Continual AI Unconf, because, well, this is pre-registration, for example, is a promising way to encourage this style of research. So I'm very excited to see what happens here. But yeah, this is generally how I used to review methods. The thing I want to sort of focus on this talk is, can we extend this sort of thinking of like clean hypothesis testing to metrics and data? This is the sort of bulk of what I want to talk about. So let's focus on metrics and evaluation first. So how do I think about metrics? Well, going back to the continual learning as treatment effects pipeline, the metrics part is when we evaluate this measure E. How do we choose this measure E? What typical online continual learning approaches do is they just report a whole bunch of metrics. They'll report average accuracy, they'll report forgetting, they'll report anytime accuracy, they'll report linear probe accuracy, and say that we're better on these metrics. And this sort of leaves something to be desired, in the sense that like what are we trying to say here? Just saying we are better is sort of not unsatisfactory. So let me like sort of say what I view this problem as, how I think we should sort of approach this problem. We should state an objective. We should use or propose a metric to measure progress on that objective, and we should benchmark. Our approaches should only be like, this is the objective, how much I have progressed on this objective, and report those results. For example, again, in this talk, I'm taking the case study of online continual learning. The objective is, I want to rapidly adapt to incoming data. This is the goal of all online systems, because if you didn't want to rapidly adapt to online data, you could just store all the data and then like learn more slowly. However, if you look at metrics in online continual learning, all of these 4 metrics, none of them measure rapid adaptation. They all focus on measuring catastrophic forgetting, which was very important in these offline continuing frameworks where your goal was to have these new generalized representations which can like work on all past data and incoming data. But it's not very suitable for online learning, where like the primary aim is that we want to adapt rapidly to incoming data. Preserving past information is fine if it helps for the new data, but otherwise it's not. Like, for example, now I don't really need to preserve information about how to use those old dial phones and things like that. Like, there's a lot of information we can forget. All we need is, on the incoming data, how do I perform well? And that's what we want to measure. So we sort of like originally started using approaches, like we started copying these traditional online learning works, where how do they measure rapid adaptation? They say, we will measure the model's performance on the next incoming sample or the next incoming batch. So the process is something like this. To get a sample, you predict on it, and then you get the label, and then you train with it, and then you get another sample, you predict on it, you train, you get this label, you train on it. You do this predict, train, predict, train, predict, train again and again. And this way you get this nice cumulative accuracy curve, and that's how you measure rapid adaptation, because this quite literally says how effective are you predicting the next data point. This is very nice. This is very clean. This was proposed in Kai et al. 2021 ICCV, and this was very nice. And so people tried using this approach. However, if you notice, this is very impractical in the class incremental OCL setups, which a lot of works have been focusing on. That's because the next sample that you get is of the same class by design. Hence, the first thing we need here is we need new benchmarks. So we sort of try to create these new data sets. We use the continual geolocalization dataset from Kai et al., which does geolocalization at scale. This is very nice. 39 million time steps sort of really tests your model ability to continually learn in like a lifelong manner, in a very long time span manner. And we created a short version of this dataset called Google Landmarks V2. The advantage of Google Landmarks V2 is that it's more established benchmark. We just took Google Landmarks and we arranged data by the timestamps. So now this is just simulating how samples are arriving on the server. These both datasets have different sources, they have different classes. So this was nice a problem to investigate. But what we found is that the stream labels are correlated. And like we thought about it for a second, and we were like, oh, this is going to happen in a lot of these natural online streams. For example, take videos. If the next frame is going to be very correlated to the current frame. So what happens? So what we are scared of is predicting on the next frame. The best thing you can do is just use the current frame, because if you get the labels for the current frame, that's almost solving the problem entirely. Let's look at real clock samples to motivate this. You see, like a lot of these images are sort of photos taken by the same person, but just like and they upload it, and then this is how the stream is constructed. So a lot of these labels are like quite correlated. A lot of these images are quite the same, and this is a problem. First, we need to demonstrate that this sort of biases the online continual learning algorithms in an important way. So we take a blind classifier. A blind classifier is a model which has never seen any data. It just takes the last k labels and predicts the next label. It has never seen any data, and hence the dumb classifier. It's a bad classifier. This blind classifier performs really high. It achieves near 45-50% accuracy on a 10,000 class classification, which is insane. This is like, and on the clock dataset, it performs comparable to the state of the art, which is very alarming because this is unambiguously a bad model. It's classifying without having ever seen the data itself. So we go further and we sort of test whether deep networks can overfit to this sort of correlations. So how do people overfit? People overfit by inadvertently making wrong design choices. They sort of test a bunch of things and like these things seem to work, and it turns out the things that seem to work sort of only like influenced overfitting on this metric. For example, Kai et al. Uses FIFO sampling, and FIFO sampling sort of encourages you to only focus on the latest samples and ignore everything in the past history, and this is bad. So we tested this. We used FIFO sampling, and we only trained a linear layer so that the representations don't collapse because we just wanted to overfit on the latest samples. So we tested on the linear layer only and used FIFO sampling. And we got incredibly high numbers on the online accuracy. We outperformed state of the art by like 40-50% performance, which is insane. So this sort of, we could demonstrate that like by these design choices like FIFO sampling, we are sort of overfitting to the incoming data. And this incentivizes bad algorithms. Even after ICCV publication, there were papers submitted recently, and before and after this, which sort of use things like Kalman filters. Now, Kalman filters enforce consistency of the current sample with the near future samples. Again, we think that this is a design choice which is falling into these same traps. So, having established that this is a problem and this can bias continual learning methods inadvertently, because people just try different ideas and they're like, oh, this idea works. But like, it's sometimes by using the wrong metrics, we can sort of choose the wrong problems to solve. So instead of using the next immediate next batch or the next sample, how do we do this? Because we still want to measure rapid adaptation. what we say is take the next sample, but not immediately, but after a very small delay. How do we estimate the delay? We want the minimum delay, because if we take too far, then the distribution changes. There's no sort of point in measuring the adaptation. Like the shift has happened. But we want to take a small, like we want to take the smallest shift such that we don't get these correlations. How do we remove these correlations? We just calculate the shift by just measuring how bad the blind classifier is. And once the blind classifier goes to random, we are like, oh, the correlations are removed. Now we can test rapid adaptation without influence of these correlations, and we see vastly different results. When we give it more compute budget, we notice that like offline continuing methods, which don't even use the half current samples, half past samples buffering. It just uses all past samples. Works the best. This is quite surprising. This indicates that obviously we didn't optimize the methods enough. This is just a baseline. There's a lot of work to do here. There's a lot of things to improve here. But also, like it's this shows that these online benchmarks sort of require a lot of like rethinking of like how to do things, and this opens a whole bunch of fields. And in fast streams, turns out it's just the best to not optimize the deep network, because deep networks are really bad at learning at one gradient steps. Because if you choose too high a learning rate, you forget. You choose too low a learning rate, you don't adapt enough. And the best thing to do is just to fix the deep network and then use a KNN to retrieve samples, which is quite surprising. So this was about data. So recapping, for evaluation, we need to sort of choose what we care about, design a metric to care about it, and only focus on those evaluations. And we saw the current metric, online continual learning, and we proposed a new one, sort of correct for the flaw, so that the field can sort of go in the nice, go like smoothly in a nice direction and things like that. Thirdly, like, is how do I see problem setups? And I'll first talk about this. So how do we decide problem setups? This has been the sort of center of a lot of debate in continual learning community these days. But I'm like more like I think the progress has been very positive. I'm like quite like satisfied, happy with the thing. It's again, we need to sort of like remember that the hypothesis testing framework, and we the core question becomes how to choose assumptions, how to choose what problem to solve. And the sort of guiding principle that I've been using is like, well, we need to make some assumptions, because assumptions help us to simplify and contextualize hard problems. And this sort of allows principled approaches rather than, oh, I tried this, I tried that, and it's just these hit and trial approaches. And just much faster to think about it more nicely, think about come up with some principled directions. And so for the empirical folks, we sort of need these simplifying assumptions to contextualize the problem well. But like these assumptions, and like the question is how to think about these assumptions. For the theory folks, I argue the opposite. The assumption should reflect the real world. We can go with these like very nice, clean theoretical setups, but it often simplifies the problem way too much. And we should sort of like focus on real world problems. I've been generally like, it's been nice to just see the progression in continual learning community. The community went in different directions towards nicer setups. Went from task incremental, which was a more theoretical setup, but like much more well defined, towards class incremental, towards now blurry boundaries. There's like mixtures of setups, and now we just adapt real metadata and we just audit by time and when we use those setups. Very nice. We went from small scale testing to see what works, what doesn't work, and now we can scale to large scale things and hopefully get towards methods which the industry can use and be happy about. And like continual learning can have like a real nice impact on industry. Similarly, in terms of memory, went from no memory to tiny memory to memory limited setups. And now we can like hopefully go to memory unconstrained setups where we only care about computational constraints. This all is nice. What I want to add a new dimension here is thinking about this question, where does labeled data come from? The sort of excitement about this came from the fact that I was looking for new problems to solve. And I was quite interested in this federated learning setup because a lot of people I know and respect are like moving towards these federated learning things. So I went and asked a bunch of people, like, well, like, what are the sort of problems you face in federated learning and things like that. And they were like, well, research is usually formulated as this communication bottleneck problem. But the biggest problem we face is there is no labeled data. These sensors cannot label data on their own. Like, we cannot get these labeled data anywhere. No one's talking about this problem. People just assume that like these streams come naturally. In fact, Elias Afros stopped at a poster and also questioned this, being like, "How can you just assume that the label just comes to you? Who is who is giving you all of these labels?" And this is quite important to think about. So I was like, yes, this is quite a nice problem, and I want to solve these sort of like pressing problems that are still missing, and hopefully this will hit the field quite a lot. Manual annotation is quite expensive. This was shown in Clear 10, which was a dataset, continuing dataset actually crafted, and they sort of benchmarked these things. And they said that they required around $4,500 for just 30,000 samples. That's quite little. And that's quite a high price to pay for 30,000 samples. So we want to sort of minimize this annotation cost. This is the neglected thing that continual learning sort of doesn't consider currently. It just considers that you get these stream data, stream labeled sets, and you have to learn from. And the task is only to learn algorithms. So the first of how to formulate this setup, like how do we sort of say that like, well, like, we need to incorporate this labeling into the problem process. So we define this new task where like you give people a task labels K, and you say like, well, like give me a classifier. So this is like, for example, some company realizing that its classifier is really bad at say dog and cat class, and they were like, oh, we need to update this. Be this the like new fashion trends. The detection model is failing at detecting lampposts or something. When they identify these problems, they just come up and they're like, oh, well, this is a problem that we need to solve. And the task here is like, well, given this problem, now design classifiers. So data stream presents only a list of categories to be learned. And we are given a computation budget CT. No data constraints. You can use any public data. You can use these big foundation models, GPT-3, DALI. You can generate images, whatever. But what we need is we want a classifier which can sort of like be continuously updated, and which classifies these new set of categories or these new domain shifts, etc., given to us. And occasionally, how we'll evaluate this is that the stream will present us some test samples, and we'll see whether we are able to continually adapt this classifier. This is sort of setup we are testing. What methods to use? People have moved from manual annotation to say using these stable diffusion generated images quite recently. 2022 late was characterized by these like, oh, can we use diffusion models for substituting these labeled datasets? Sort of excitement. Recently in 2023, the excitement shifted from like, well, these stable diffusion models are too expensive. Can we just use Lion 5 dataset? Can we just retrieve relevant samples from there and just use it out of the box? This was a sort of like excitement in like 2023. There are lots of NeurIPS ICC papers about this. We go one step forward and we ask, well, Lion 5B was taken from the internet, and it's a very nice thing. It has search engines. You can actually, it's quite nicely indexed, and you have this huge source of data where billions of images are uploaded. They're nicely categorized, and these static datasets like Lion 5B are minuscule in comparison to the internet. So our question is, can we leverage these internet datasets? So our idea was really very simple. We don't do anything on the continual learning approaches. We keep that fixed. So we have just one isolated problem that we study again, which is how to add this missing label data part, how to compensate for it. And the idea is that we just download images from searching the web. This is quite traditional an idea, but like I think this is quite effective. I think like people just like sort of like get too excited by new things, like, oh, well, we have stable diffusion, so we can generate images now. And like, but like people have sort of explored this problem before. There are like nice principled approaches people use, and downloading the internet has been like this one line of research which has been going on since quite a long while. So we use internet, we query sample, we search the terms on different search engines, we download data, and then we train a linear probe or some like very cheap classifier, and this is how we get our continuing baseline. Let's first test like how does this perform with respect to these stable diffusion models with these Lion 5B retrievals. Do we get like, is the improvement substantial compared to these sort of other alternative approaches? Because some people use GPT-3, they're like prompt clip with like complicated GPT-3 prompts. Other people use the stable diffusion things and things like that. And we show that internet is vastly better. This gives us like 20, 30, 40% boosts on fine-grained datasets. We choose fine-grained datasets because they're quite hard. It's easy to imagine that you can get a lot of data for cats or dogs, but getting a lot of data for Epicene cats versus German shepherds versus very other specific breeds of dogs in a noisy setting where like internet is quite noisy, it's very easy to confuse. Can internet do this? And it's surprisingly yes. Internet can do this. Internet can do this very well. And so this is sort of the clean approach we propose. But in this talk, I want to sort of step back and sort of focus on the general framework. We only focused on one part of this problem. We didn't sort of innovate anything on the continuing approaches. We just said, let's focus on where's data. We sort of tested approaches for where's data. We proposed a new approach for where's data and showed that it improves performance. This is nice, clean, sort of these hypothesis-driven testing and like these isolated testing parts. And hence, we always almost end up with these simple, clean methods, which hopefully are of use for the community. This was my short talk. Any questions, comments, feedback? I have this anonymous feedback link as well, if people are interested. But yes.
Great, thanks. Thank you so much. I'm very curious about that anonymous feedback link. So that's a very nice idea. I haven't actually seen in other talks, I guess. So actually having the opportunity to leave an anonymous feedback to a presentation and to an author in general is quite nice.
Yes, because I guess, I don't know, people are slightly scared of like, well, about saying bad things about papers. So I was like, you know what, you can say bad things about my papers. Just send like anonymously without. So I can get the valuable feedback being like, oh, well, look, computational budget is not really the focus in these embedded systems. IO budget becomes the issue and things like that. Like it's the only way to find out is to get feedback, and I really appreciate this feedback. Questions?
Yeah, I guess we have a lot, a lot of questions. Your talk really sparkled some attention, to say the least. So let me start from like chronological order or something. So I see also some hands raised. So we're gonna go there, unless it's okay. No. Yeah, Marty, you actually asked two questions and you have your hands raised. So I guess if you want just to unmute yourself and perhaps ask a general question, a comprehensive one, you should be able to do so. All right. In case I'm gonna just read the questions for the moment. So Martin first asks, perhaps might want to find another system that A matches better with. I guess this was related to the first part of the talk. I don't know if this is enough context to reply to this first answer. You might want to find another system that A matches better with. And also, let's not forget that greater complexity is equal to a higher VC dimension. So you need more data to validate A's contribution. So I guess that's more related to the ablation style. Yeah, exactly. I'm not sure I understand very well the question, but if you do, I can answer.
Yes, I don't know exactly. Like because probably I'm like more of a systems person. I have slightly disconnect with the theory questions usually, but
yeah, I guess the point is that when you allow for a model to become more complex, so probably adding all these components A1, A2, and A2, A3, and so on, the VC dimension increases, and the VC dimension just, expresses the complexity of the system, so the model can overfit more easily, and you need more data to train and evaluate.
Right. Like the sort of focus of this was not on like, yes, like that's why people typically prefer to test on big data sets. But I think like with deep network, somehow this is not a problem. The sort of core issue here is this garden of working paths. You can almost always make like, I mean, not almost always, but like said, there's with some tricks, you can always make some complex system work, get some higher performance. And this is the sort of thing that we don't need to do. And like, with principled approaches of this hypothesis testing cleanly, these sort of garden of forking paths is avoided. Pre-registration as well is like sort of one way of avoiding garden of forking paths. That's why I'm very, very curious to know about like how these work. But that's my sort of my concern about these big models, like about these complex models. Is like, well, you can always make these work in some way, usually, and that's a problem. It doesn't say that the actual idea is better.
Yeah. So Marty has another question. I'm just looking at them in order. I wonder if it makes sense to include in our set of metrics measures that focus on outliers, so robust statistics, to get a better sense of the long tails. Outliers often have serious impact on mission critical classifiers. Well,
Yes, by all means. Like I as long as the goal is clear that like you want very critical classifiers, so the goal there is like, well, you don't want it to incorrectly classify. Maybe it's okay to just say that like I will not classify anything, but we don't want incorrect classifications because there might be catastrophic. If that is a scenario, then it's really like if that's the objective, then like you sort of like have these metrics where like you really pose high costs on the rejection things or like high costs on the long tail and things like that. So for example, using F1 like macro average F1 across classes and things like that is nice. This sort of there is this really nice discussion by Peter Flack. There's lots of talks from Peter Flack from University of Bristol about this, which I really love.
Yes, I think I've seen this only in like adversarial learning and continual learning, but I think it's a very nice idea to consider also outlier. Martin, you have your hand raised. You want to ask a question?
Yeah, I'm kind of going to say something which is related to what Marty had written on the sort of set of metrics that measure more on like outliers, robust statistics, data queries, and so on. Because I do think this is a very valid question that people have been working on for quite a long time, even in continual learning. And somehow, I mean, you're asking for feedback. I don't need to give it anonymously. Somehow I got the impression that like 10 years of literature by a lot of people, including some of the people talking at this conference, is ignored in that perspective. Like, I'm not sure this idea of sort of we should get a metric and then kind of do hypothesis testing based on it and kind of tune that to death is valid. Like I'm wondering,
Yes.
I mean, the entirety of open world learning, for instance, like it actually says you should be querying data, you should be detecting outliers robustly and do continual learning. And the number one reason why they say that is because all of the present continual learning literature has kind of emphasized single metrics so much that they forget all the other important parts, and then the systems essentially become useless, right? So
yes.
I was a bit surprised, to be honest, to not have this perspective in your talk.
Yes, I was slightly worried about length, hence this was the issue. But yes, sometimes two metrics are like competing with each other, so you need to have these Pareto optimal like whatever trade-offs between the metrics. Things are a lot more complex than I put. Like this is just if I just want people to just like not just report 4 metrics and not do anything about it. But like yes, like sometimes metrics compete. There are issues with metrics. Like sometimes when you keep optimizing a metric, you just good hurt the objective. Like the metric sort of ceases to be a like a good proxy for the objective that you wanted to use. All of this is very valid. In fact, I am now like sort of starting to work on more active problems because I'm like, well, that is very like it should be more of a bigger part in like continual learning. So I'm quite excited about active learning and like these open world tasks. Yeah. So I completely agree. Yes. I will add these points in like an extended version of the slides. I usually just make an extended version.
Yeah, sorry, we also had a limited time for you, but I mean, I get Martin's comment, and it's for sure useful. Yeah. I mean, to add some more context to the presentation. Nilay, I allowed you to unmute yourself. You have your hand raised. So if you want to ask a question, please go ahead. Okay, I guess not. So we can go ahead. We still have time. So questions are keep coming. So that's a good sign usually. Nishant asks, could you please talk a bit more about your thought process in designing targeted metrics for your objective? What is the way of thinking you use? Or can you point to some framework that helps you think about designing metrics?
Yes, if I have to point to a framework for how to design metrics, I would just point to Peter Flack's work. It's very nice. He just like talks about when to use accuracy, when to use F1 score, like what are these differences, because like in classification literature, people have been like just reporting these metrics without thinking what they sort of measure. So it's like it's kind of important to connect metrics to like what is this metric trying to measure? Do I want to measure it? What are the trade-offs I want to have in my system, and what is the best proxies for doing that?
Thank you so much. There's another question from Hamed. The computational constraint necessity is definitely reasonable, but how is the unconstrained memory assumption realistic?
Yes, I have been sort of wondering about this because what I've seen in these real world systems is that they're almost always compute bound. My mobile has like a terabyte of uh storage. They are like mammoths. They're like SD cards you can buy for terabytes, but like I can't do a backward pass on it. It's just too expensive. Like like any and like NVIDIA Jetsons and things like that. They have GPUs, but like you can just connect hard disks, and like hard disks can become very big. They're really cheap. I've never seen any sort of memory constraint really. Like there are IO constraints sometimes, but never. When I say memory, I mean hard disk storage. That's super cheap, and like by these like data loaders things, you can sort of like load things quite nicely. The sort of issue is that we don't have compute, and if you see these papers, often that they train for 90 epochs, 200 epochs, especially offline continuing directions, and that's sort of like I think the bottleneck. What for example, GPT-4 stores everything you type into it, etc. But to update GPT-4, they need humongous amounts of compute. So if we can propose strategies which use less compute, it's super useful in like these applications.
Thanks. I'm afraid we're not gonna answer everything, at least not live, but let's take one or two more. So which areas in industry do you feel would be able to actually benefit from continual learning in the near future, and in what form?
So I like
That's a
so
tough one.
I always like this sort of like approach by Professor Tina Tutlias. With she gave this in a collage talk recently, which is like, oh, like well, like continuing has different objectives. Like so, different objectives suit different parts of the industry. It's not like a one like it's like a group of like people who sort of want to do the same thing but slightly different things. So like some people want to focus more on like embedded systems. Some people want to focus on, well, I have like a server and I'm practically usually like querying these like I say for example I'm a Flickr server and I have to respond to user queries. Some people want to focus on these large models, like how do you say for example how do you update GPT-4? That's their primary question. So depending on the setup, like depending on the problem you're tackling, the approach slightly varies, but I think the things they have all in common is that compute is constrained, memory is relatively unconstrained. Like videos, it becomes slightly bit of an issue, but like still their compute is the bottleneck because you cannot compute on all video frames. I like to pick these like common trends across these setups, but keep everything else the same.
Yeah, and I guess this holds also for online continual learning, because we have a question which asks to specify this application or relation to industry with respect to online continual learning, but I guess that's mainly the same, right?
Yes. And just to add
Yeah.
that, like, yes, like I have been a big fan of open world learning approaches. I originally started my PhD wanting to work on open world approaches. I've just sort of constrained myself to like the closed world thing because I'm like, first, let's solve this problem, then we'll add active component, then we'll add the like OD detector component, because usually open world problems are like, well, classify whether it's auto distribution or not, and then like then you have this like data classification, then you can do this active learning, things like that.
Yeah, so let's take the last one, since you were very quick in answer. Thank you. Would it make any sense to use multiple reference classifiers for labeling and continuously train an ensemble of online classifiers? Like,
Classifiers for labeling. So the ground, like, is the
yeah.
assumption that the ground truth labels aren't there? That's sort of a prediction. That's sort of what happens in deployment, I presume, because like you don't get any feedback and you can't improve. There is some work on test time adaptation for like, well, how do you sort of like adapt a test time, maybe? But I have been slightly pessimistic because I saw this paper called Ardam, and like it's just the issue with test time adaptation is that of collapse, and collapse happens really fast. And like I see no long terms, like it's like over a period of time it'll just happen, like you have no option but to just reset. And I don't know of any better alternatives there, unfortunately.
All right, great. Thank you, Ameya. Thank you so much for your patience in answering all the questions and your availability. It was really a nice talk. I think we should have more talks like this, talking about the way we do science, basically, and how that impacts then on our results and on our evaluation protocols, which are always key when you present a paper and discuss more than one result at a time. So thank you again. Thank you so much.